Hi everyone, hope you're doing well. The aim of this lecture is to address some questions related to Pauli matrices and basis transformations. So let's do it. First of all, the Pauli matrices are defined this way in the basis which diagonalize the sigma z matrix, and this basis can be represented this way. The plus or the up state is 1, 0. The down state or minus is the 0, 1. It's obvious, pretty obvious here. And there are two eigenvalues, the plus and the minus 1. The plus 1 corresponds to this eigenvector. The minus 1 corresponds to that eigenvector. All right? I guess you can see it clearly. And what we are going to do right now, we are going to find the eigenvectors and the eigenvalues of the sigma x. All right, you can do that for the sigma y. It was asked in the previous lecture, I guess. But let's go. Let's do the work or the job for the sigma x. So sigma x is equal to 0, 1, 1, 0. So how do we determine the eigenvalues of this matrix? First of all, we take the determinant of the matrix minus lambda, some parameter. You can put it here, multiplying the identity matrix, which in this case is a 2 by 2 identity matrix. It must have the same dimensionality of the matrices. So if you write this equation, you need to calculate the determinant of this matrix. It's the sigma x, which has ones in the off diagonal terms, and the minus lambda will appear here in the diagonal, and you need to set the determinant equal to 0. So the determinant of a 2 by 2 matrix is really easy to perform. You multiply these principal diagonal parameters minus the off diagonal parameters. So you'll have the equation lambda squared minus 1 equals to 0. And here you will find two possible eigenvalues, which corresponds to lambda squared equals to 1. So lambda is equal to minus or plus 1. So the same eigenvalues for sigma x as for sigma z. All right, they are the same eigenvalues. And for sigma y, if you calculate that, you'll find sigma y, it's minus I here and I here. You'll find just same eigenvalues. So for all the Pauli matrices, the eigenvalues are plus and minus 1. All right, so you now can calculate the eigenvectors. So the eigenvectors of a sigma x matrix may be calculated this way, right? You have a sigma x matrix applied to a vector which has two components, a and b, say, is equal to one of its eigenvalues. You need to calculate two eigenvectors, one corresponding to the plus 1 and the other corresponding to the minus 1 here. I will calculate them here. So if you put a minus or a plus or a minus 1 here, you will find the eigenvalues. All right? So let's do that. For the plus sign here, you'll find here you can write explicitly the matrix. So 0, 1, 1, 0 here, and then you multiply it. A equals to 0, 0 multiplying A, it's just 0, plus 1 multiplying B is just B, is equal to the corresponding line here, which is the lambda multiplying A. If I choose first the plus sign, I'll have B equals to A. In the other case, I'll have B equals to minus A. And there is no need for perform the other equation because it will produce the same thing, which means A equals to B or A equals to minus B if you choose the minus eigenvalue. So for lambda equals to plus 1, you will have this equation. For lambda equals to minus 1, you will have this equation. B equals to minus A. So you can choose any value you want. Eigenvectors are defined apart from some multiplicative constant. So there are infinite number of eigenvectors which are distinguished by only a multiplicative constant. So the ratios of the components are the same for any choice you can do. So let's plug in A equals to 1 and are corresponding to the plus in the x direction, which means the sigma x matrix. Let us call this eigenvector the plus comma x, which means the corresponding to an eigenvector of the sigma x matrix. 1 for A and 1 for B, right? And for the minus, I'll have this equation. If I put A equals to 1, B will be minus 1, right? So 1 minus 1 here. But notice that this vector is not normalized to unity, and it must be the case for quantum mechanics. So in order to normalize, it is a thumb rule. You can do it always. You just divide your chosen values here. You write the eigenvector, and now you just divide by the sums of the modulus of these numbers squared. So the square root of 1 squared plus 1 squared, it's a number 2 here. All right. And here the same thing, because it's 1 squared, just 1, minus 1 squared, just 1, sum them up, you'll find a number 2 here. So these are the eigenvectors, the eigenstates of the sigma x matrix. This corresponds to the plus 1 eigenvalue. This corresponds to the minus 1 eigenvalue. All right? It's how it's done. When you perform it's important to mention that when you perform the calculation of the eigenvalues of a given matrix, suppose the matrix A is n by n, a matrix with dimensionality of the Hilbert space, which is n. In our case here, the n is just 2, but it can be any value here. You'll find for discrete systems with finite number n, you'll find n distinct, or maybe not distinct, n eigenvalues in general, all right? N eigenvalues. And for the eigenvectors, you will have an eigenvector of the form for a given lambda. This equation is equal to 0 here. This equation will be an equation of the form lambda elevated to some n here plus some coefficients here, which will depend on the matrix parameters here. You can write an equation, so coefficient C1 lambda n minus 1 plus a C2 lambda n minus 2, and dots must be equalized to 0 here. But for a given lambda, you solve this equation, you will have n roots, and this is the origin for n eigenvalues. If you choose a given lambda, you have to determine the equation for the eigenvector. So you have an equation of this form, the lambda eigenvector. For that lambda eigenvector, it corresponds to that eigenvalue and the eigenvector. The eigenvector will have n components, a constant, say psi1, psi2, psi n. But in the determination of these amplitudes, you will need just n minus 1 equations. The last equation or the first equation, one of the equations is redundant. So it is not linearly independent of all of the other equations. So you will find relations between these numbers here, right? These are complex numbers in general. So n minus 1 equations which determine only the ratios between psi1 and psi2, and the ratios include the modulus and the phases, psi1 and psi3, psi1 and psi-n, and so on, right? So in our case, in the present case here, we are talking about Pauli matrices. Dimensionality is 2, and there are two eigenvalues, in this case +1 and -1. It's important to say a few things about matrices. These are properties. I'll call it properties of matrices. Right? Traces. A trace of matrix is, and the determinant of matrix, which means the eigenvalues are independent on representation. So if you have matrices and you perform a basis transformation which transforms the components of the matrix, the eigenvalues will not be changed at all. And eigenvalues are encoded in trace and determinant. The trace of a matrix corresponds to the product, the sum of all of its eigenvalues from 1 to the nth component, nth eigenvalue, and the determinant of a matrix is always equal to the product from 1 to n of its eigenvalues. All right? So these two properties of a matrix, of a given matrix, are independent of the representation being chosen. So of the basis which you use to represent the matrix. It's very important. You can change the representation, the eigenvalues will be the same, all right? That's very important. Property of matrix. But there are another concept, mathematical concept, which is degeneracy. I hope it's right. It's right. Degeneracy. I hope I wrote this correctly. But degeneracy of an eigenvalue of eigenvalues corresponds to the number a given eigenvalue is repeated. So if you can find a diagonal form of a matrix, it will have the eigenvalues in its diagonal and zeros otherwise. So off diagonal terms are zero. You can find a basis for which you can put for a given matrix all the eigenvalues in the diagonal of that matrix. All right? But if suppose lambda1 appears, a value lambda1 appears 2 times or 3 times or n times, distinct from, in general, is distinct from this n, the dimensionality, but in the limit it could be the case. This, in this example here, lambda1 appears 2 times. It is called the degeneracy of that eigenvalue. So an eigenvalue is n, not the same as the dimensionality, is n degenerate if n is greater or equal than 2, and this is the level of the degeneracy. All right? If a given eigenvalue appears only one time, it is said non-degenerate. All right? Non-degenerate. And it's very, very important because if you have two eigenvalues or one eigenvalue repeated twice or 3 times or as many times as it appears in the diagonal of that matrix, if you have a diagonalization process and put the matrix in this form, right? That corresponds to n distinct eigenvectors corresponding to the same eigenvalue, the same value of the numerical value for the eigenvalue. All right? So suppose for an example, A equals to 1, 1, 2. Suppose this matrix here. It's an example of a matrix, diagonal form. What are the eigenvalues? The eigenvalues of this matrix are 1. The set of eigenvalues are 1, 1, minus 2. And the 1 appears two times, so it is degenerate, doubly degenerate eigenvalue because it appears twice in the matrix. And therefore, there are two distinct eigenvectors corresponding to the same numerical value of an eigenvalue. And in this case, you could choose the state 1, which is 1, 0, 0, the state 2, which is 0, 1, 0, and the state 3, which is 0, 0, 1 in the end. All right? And these two eigenvectors corresponds to the same numerical value, the same eigenvalue, say, right? And this third eigenvector corresponds to the last eigenvalue, which is -2 in this case. All right, so degeneracy is eventually a property which is normally related to symmetry. When you have a highly symmetrical problem, it will generally correspond to a high level of degeneracy of the eigenvalues. And also, if you change the representation, this matrix could assume another form with non-zero values here. The diagonal values change also, but the eigenvalues and also the degeneracy of the eigenvalues do not change by performing a matrix transformation or a basis transformation. All right, so it's a property of the matrix. The eigenvalues do not change, and so therefore the degeneracy of the eigenvalues also is invariant respective to a basis transformation. You can transform representation, but the eigenvalues do not change, right? Well, let's go back to the problem of Pauli matrices. So we were talking about eigenvectors of this one and the eigenvalues. We already know there are two eigenvalues, plus one, see the plus eigenvalue, minus one, and this corresponds to the vectors plus in the x direction, minus in the x direction. And notice that a plus, which is 1 over the square root of 2, 1, 1, can be written as 1, 0 plus 0, 1 here. All right. And this is just the up state relative or the plus state related to, I'll put it explicitly here, related to the Z matrix, the Z Pauli matrix. And this number here is a common factor, and this vector here is the minus, corresponds to the minus eigenvalue related to the Z component of the Pauli matrices. All right, so if Pauli matrices are in the diagonal form, these are the basis 1, 0 and 0, 1. These are the basis vectors of the Z matrix. And the plus eigenvector corresponds to this thing here. And the minus eigenvector is just 1 over the square root of 2, 1 and minus 1 here. So you can write it as a plus Z minus a minus Z eigenvectors. So notice, and I am anticipating this Pauli matrices have to do with spin of spin half particle, and in this case the spin up projection in the x-axis is just a linear combination of up and down spins related to the z-axis, and also the down spin related to the x-axis is a linear combination, but with a distinct sign from the previous one, of up and down z spins, spin projections, to be clear here. All right. So if you use this basis here, which corresponds to these vectors here, you can make a basis transformation which just representing the matrix in that basis. You can perform that in distinct languages. You can use this resolution of identity in any basis do you want. So the resolution of identity corresponds to lambda equals to plus and minus, plus and minus, plus or alpha in the x direction, alpha in the x direction, or also you can represent in the other basis which corresponds to the vectors or the Eigen Vectors which diagonalize the sigma z. So this identity can be represented in any given basis, a complete basis, all right? Notice that plus in the x direction projected to itself gives 1. It's the same for the minus. And minus projected to the plus in the x direction gives you 0. But if you project, for instance, plus in the x direction into minus in the z direction, you'll find 1 over the square root of 2. Taking the modulus squared, 1/2, which means the probability of measuring the up state in the x direction given the down state in the z direction is 50% in the percentage value. All right, so you can calculate the percentages. And you can also, so notice the orthogonality is valid inside a given basis, but if you project a vector in one basis into the vector of another basis, the orthogonality is no longer valid, okay? So you can perform basis transformations. Suppose you can represent sigma x, sigma y, and sigma z in a given basis. All right. For instance, in the basis which diagonalize this matrix, you just need to put the identity, the matrix here in the representation you already know, and the identity here, and this will be your components here of that matrix. All right. But the components here, say the component 1, 2, 1, are just projections in that given basis. All right. So in this case, I'll perform the calculation explicitly using the vectors. So I must say that sigma of x in the basis of x corresponds to plus x plus x here. This is plus x minus x plus x minus, sorry, minus plus here, minus minus here. Well, we can change x by z, x by z here in the matrix, and you will representing in the x basis the sigma z matrix, and all other matrices you want to represent, you can do that. All right. So you need to calculate for sigma of x. You know there are eigenvalue and eigenvector and orthogonality relations. So if you use the plus eigenvalue, it corresponds to +1. Repeat the eigenvalue. If you apply it to the minus eigenvector, it will give you the minus eigenvalue, and repeat that eigenvector. So if you project now this equation with the plus bra in the x representation, the vectors in the x representation, you'll find out, for instance, plus in the x representation is sigma of x plus x is just 1. Why is that? Because you project here, this is an eigenvalue and eigenvector equations, or an eigenvector equation. So find out a plus 1 is just a number, and you project out this state. It gives by the orthonormality of the basis a 1, so you'll already have 1 here. The same you can do for instance, plus projecting the sigma of x with this other equation here. There are 4 combinations you can do, and you'll find that this matrix operating to its own eigenvector corresponds to its eigenvalue and repeat the eigenvector, but the orthogonality of the states, you can prove they are orthogonal, will give you this applied here gives a -1, repeat this thing, and when you project the plus state onto the minus state, gives 0 because of the orthogonality inside the given basis. And if you do the math for a projection with the minus here and the plus here and the minus here and the minus here, you'll find out another 0 and a -1. So in this case, you can demonstrate the sigma x in its own basis, using its own eigenvectors, is represented this way. It becomes diagonal. And this is what we call the diagonalization of a matrix or of an operator. All right? We find out the eigenvectors which put the matrix in the diagonal form. So the eigenvalues appear in the diagonal of diagonal terms will become 0. All right? Also, you can calculate the components of sigma z projecting. There are 4 calculations needed: plus x, sigma z plus x, plus x, sigma z minus x, minus sigma z plus and minus sigma z minus, right? There are 4 numbers which are the components of the matrix, sigma z, represented in the basis which diagonalize the sigma of x. All right? So sigma z will not be diagonal in this basis, because why we can already know that? Because if we worked out the algebra, we know that sigma of x and sigma z is distinct from 0. All right? It's different from 0. These two operators do not commute. They are incompatible. So if you put sigma x diagonal, sigma z will not be diagonal. If you put sigma z diagonal, the other matrices will not be diagonal. All right? You can calculate for sigma of y also and just find out what happens. But in this case, you can find that the sigma y is just non-diagonal also, but it does not change its form in this basis of plus x and minus x. All right. So you can do the math. You can perform the calculations in many distinct ways. You can represent this in the z basis also, or you can do just write 1 over the square root of 2 appears twice because it comes from here and comes from here. So you can drop out the square root and you get a 1/2 here. So you can put the complex conjugate and transposed of this vector. It is 1, 1, so it becomes a row vector 1, 1, 1, 0, 0, minus 1, 1, 1 here. You'll find out 0 for this calculation. You'll find out 1 for this calculation. You'll find out 1 for this calculation. You'll find out 0 for this calculation. So in the basis which diagonalize the sigma of x, sigma subindex x, which corresponds to the Pauli matrix, which measures the spin in the x-axis, this matrix will be non-diagonal. Coincidentally, it has the form of the sigma x in the basis, which puts this matrix in the diagonal form. But it's just a coincidence here, all right? It's nothing more profound. As a matter of fact, we can perform a rotation around the y-axis. I don't remember, I guess the angle must be 90 degrees, and you rotate the x and z matrices, and the sigma y in the both bases are equal. All right, so sigma y doesn't change. You can perform a calculation, plug in sigma y here, and perform the math. Just change the numbers here, and you'll find out 0 minus I 0. So a change of basis does not alter the content of the eigenvalues. The eigenvalues are the same, but for non-compatible operators, if one of the operators is in the diagonal form, the other will not be. And you can change the basis and put the other one in a diagonal form, but the original diagonalized matrix will be off diagonal. Now it will have non-zero, non-vanishing coefficients in the off diagonal components. Right? So I guess it's clear. A basis gives you a matrix representation of a given operator. If you change the basis, you change the components, the specific components, but the degeneracy and the eigenvalues are invariant of that matrix. All right, they cannot be changed by a basis transformation. Okay. So remember this thing here, written in a more elegant way. They do not commute two of the Pauli matrices. It's twice the imaginary unit, the Levi-Civita tensor sigma of k. As a matter of fact, when you find repeated indices, an Einstein summation is implied, which means when you find usually in physics, except stated otherwise, when you find something like this, and A, it can be a vector having components alpha, indexed by an alpha, and the vector, or B, alpha here, if the index is repeated, usually in many places, they do two-dimensionally here, they don't write the summation symbol, it's implied. So it is called the dummy index convention. If an index is repeated, k here is repeated, it's implied that you must sum over that index, all right? So it's implied here, the summation. But you, in this case, do not need to sum over because all the specifying I and J, all the other case, which the other values of the K variable here, which are equal to J and I, will produce a zero result. But as a matter of fact, if you have repeated indexes, you must sum over them, usually. All right? So this is one form of the equation. The other is the anti-commuting equation, right? This is twice the Kronecker delta. I and J here must be interpreted as some, you must choose between X, Y, and Z here. You can choose among these directions here. So if you choose, for instance, I equals to X and J equals to Y direction, you'll find out twice the imaginary unit. This is the imaginary unit. Do not be confused by this subindex here. This is just an index, indexing the component of the Pauli matrices, or the specific Pauli matrix you are choosing here. So you'll find out X, Y, the only possible here is Z. So sigma Z. Sigma Z. Well, the K can be put here, all right? It's not a big problem. So this is an equation, specific equation when you choose I equals to X, J equals to Y. And if you choose I equals to X, J equals to Y here, you'll find zero. So Pauli matrices anti-commute with each other. All right? It's a very important result also. And any matrix product, notice the following thing. Any matrix product, A multiplying B, two matrices, you can write it in the following way. 1/2 of AB plus 1/2 of AB plus 1/2 of AB minus, reversed order here, minus 1/2 of BA. Notice this summation gives 1 times AB, and this summation gives you 0. So if you organize, recast the things as follows, pick these two things together and these other two things together, you'll find that AB, the product of two matrices, is always half the commutator, which corresponds to half AB minus BA. So it's the commutator by definition, plus 1/2 the anti-commutator, which is AB plus BA, the anti-commutator. This is a general result for matrices, valid always valid, okay? It's a general result here. I'll ask you for general matrices to demonstrate the following. Demonstrate A, B, C, three operators here. You can find this is A, comma B, multiplying C, A minus B, all right? I I guess it's a plus here, but you can also use the anti-commutator here and find this. Right? The A can be commuted with B and multiply C, and the B goes in front of everything. A commutated with C, and you can use anti-commutators, but the sign here changes. You can demonstrate this thing. You can do that explicitly because this thing here is ABC minus BCA. So you can perform that the previous tricks of inserting sums and differences of terms which cancel out and allow you to write a commutator here, and you'll find a way to demonstrate that. All right, you can do explicit calculations also. You can multiply everything here and find that an identity. All right, so demonstrate this important result for operators or the algebra of operators. All right, I will have it as an exercise. So let's go back to Pauli matrices. It's a very interesting problem with or using matrices, because if you have this thing here, a Pauli matrix multiplying a vector A multiplying a Pauli matrix which is dotted with a vector B. So a vector is a vector in the three-dimensional space. It corresponds to components AX, AY, AZ, and the B is a vector BX, BY, Z. All right, they are just vectors. You can use real vectors if you want here. They can be real vectors or complex eventually, right? So you must interpret sigma vector dot the vector A is equal to sigma x AX plus sigma y AY plus sigma z AZ. And if you write the matrices here explicitly, you'll find out the same for B, right? You'll find out that the Pauli matrix dot the vector A corresponds to a matrix representation of the vector, which puts the Z component in the diagonal, all right? And puts X and Y components of the vector off diagonal in the matrix. If you calculate the trace, it gives you 0 in this case. All right, this the trace of all the Pauli matrices are 0 because there are two eigenvalues for any of the matrices. So if you sum the eigenvalues, it's +1, -1, 0. So the trace of Pauli matrices are 0. You need to multiply it by another Pauli matrix to find out what happens. But for this equation, the trace is 0, but the determinant of this thing gives you minus AZ squared minus this thing multiplied by this thing. It is just minus A subindex x minus A subindex y squared, and this is just the negative of the scalar product of the vector with itself. All right, so this is the negative of the scalar product here, the determinant of the matrix. Also for B, if you sigma dot B, the determinant will be the negative of the scalar product. Suppose these vectors are real vectors, all right? Just enough for now. So this is an important property. So what is this thing? A sigma dot A, sigma dot B. It's a matrix product of a matrix of that matrix with a matrix with B's. All right. What is this product? We can perform that explicitly, but it's not so interesting as if we use some algebra here of the Pauli matrices. So sigma dot A, sigma dot B, I can write it as a summation from the index I equals to 1 to 3, or x to z here, if you prefer, x to z. I will not put this in all the summations where it is implied. So for the first, sigma I, the vector AI component, and the summation, I change the index, j here, sigma j, b, j. All right? Summation goes from x to z. All right? So I can put the summations in front of everything, summed over two indices, a, I, and j. The components of the vectors are just numbers, so I can put in front of everything, and I'll have this thing here, sigma I, sigma j. All right? And that I can represent this way. Sigma I and j is equal to a subindex I, b, j, 1/2 of the commutator plus 1/2 of the anti-commutator of these two matrices. It must be summed over, all right? And this, I already know what it is. It's twice the imaginary unit. Now it's the imaginary unit, not that index. The Levi-Civita permutation symbol here. This thing here is twice the Kronecker delta, I and j. So in this case, I can rewrite this thing. Notice that the number 2 cancels out. So I'll find out a summation over I and j indices. This thing here, which was already there, the Levi-Civita symbol multiplied by the imaginary, the Pauli matrix sigma k plus delta E ij. All right, that's it. And now I can sum these things. I can sum, but if you look at vector algebra books, the summation over I and j and k, because it's repeated index here, is just the definition of a triple scalar, scalar, I guess. That's it, vector of vectors. And so this first term, I can write it the imaginary here, the vector of Pauli matrix sigma dot a vector b. Okay, this is the symbol for this thing here. And if you perform the summation, you can sum over the j, but this delta ensures I equals to j. So the only possibility is when I is equal to j, and you can replace the j by I, and remove a summation over j, but the summation over I means A of I, B subindex I. This is the scalar product of two vectors A dot B. So this thing here multiplied by this thing here and summed over I and j is just a scalar product. You can find out in linear algebra books also, which work with vectors. All right, so this is a very important result for Pauli matrices. For Pauli matrices, sigma dot A, sigma dot B, in the vector notation here, corresponds to the scalar product of two vectors plus the imaginary unit, the Pauli matrix dot A vector B. That is demonstrated. All right. So also you can demonstrate this identity promptly or straightforwardly, because if you have this thing, the exponential of a matrix with an angle theta divided by 2, this thing here, all right, notice that it is a unitary matrix because U dagger, the transpose conjugate, you just change the sign of the imaginary here. The Pauli matrices are Hermitian. The n vector is a unit vector, a real vector. Theta is a real number. And this thing is the inverse of that. So U dagger U is equal to the identity, a 2 by 2 identity in this case. So this is a unitary matrix. I didn't mention that previously, but unitary matrices can also be written as the exponential of imaginary multiplying any A matrix here, satisfying this condition. A is Hermitian. So a unitary matrix is the exponential of the imaginary times a Hermitian or self-adjoint matrix. This is called Hermitian condition, or also self-adjoint. But in quantum mechanics, the term Hermitian is oftenly used. All right. So if I want to calculate this thing here, this exponential here, what I must do? Well, I can plug in the resolution of the identity resolved in the eigenvalues of sigma dot n. I can do that. But also, so I have eigenvalues of this thing. Again, I have the plus eigenvalue, which corresponds to a plus sign, plus 1, sigma dot n in that direction, in the n direction, suppose. And plus here, I have eigenvalues, sigma dot n, a minus component, minus 1, the direction of sigma dot n minus. All right. I guess in Sakurai's book, there is an exercise asking you to show something like this, all right? But there is another way of calculating that. So if I want the exponential, this exponential, I can expand it as a Taylor series. So I have the identity plus the operator plus 1 over 2 factorial, the operator squared, plus 1 over 3 factorial, the same operator to the third power, plus dots. It goes forever, all right? But notice this thing squared, if you calculate this thing squared here, it corresponds to multiplying the matrix by itself. Theta is a number, 2 is a number, the imaginary is a number, the only matrix is this scalar product here. So I can use the previous identity. So the A is n, the B is also n. So I have n dot n multiplied by the identity matrix. All right. When you are dealing with matrix equations and you have something which does not like a matrix, just like it seems like a scalar, it is because it is implied the multiplication by the identity with the correct dimensionality. So you'll have a dot b, but a is equal to b, plus the imaginary sigma Pauli matrix vector dot n vectorial, the cross product, n vector cross n. And we know the cross product of a vector with itself is just 0. And also I know that this is a unit vector, n dot n by definition is a choice, is unit vector, n is a unit vector. It corresponds to the rotation axis. You rotate things by the axis n in space. It can be any given axis. It's arbitrary. And it's unit vector distinguishing that axis from the others. This is 1, so you have the identity here. So any time you find even products of even number of repetitions of this operator, you will find the identity. And the odd powers will have an even number multiplied by a single one. And in this case, if you can calculate, for instance, the cube of this equation is the squared multiplied by this thing one more time. So this is the identity multiplying this thing here. So you'll find that is the identity plus I sigma dot n theta over 2. This I becomes negative. I squared is minus 1. This thing squared is the identity theta over 2, 1 over 2 factorial, plus multiplying the identity, of course, plus the I cubed is minus I, the sigma dot n cubed is just sigma dot n because the square is just the identity, so the sigma dot n theta over 2 cubed and divided by 3 factorial, plus it goes on. And in this case, notice that the identity can be accompanied by 1 minus theta over 2 factorial. It's a squared value because it comes from here. And you'll find the next term multiplying the identity will be 1 over 4 factorial, theta over 2 to the 4th power, and so on. The odd powers will be theta over 2 minus theta over 2 cubed. The next term will be the 5th power, and these are the cosine and the sine functions. So it's demonstrated that multiplying the identity, you find the Taylor series for the cosinus of theta over 2, and multiplying the imaginary sigma dot n, you'll find this sinus series, the series for the sinus function. So it is demonstrated this way that you'll find it to be the identity, which is oftenly neglected or omitted, to be precise. Cosinus theta over 2 plus I sigma dot n, the sin function theta over 2. This is a generalization of this Euler equation. Divide by 2 here. Right? This is a generalization. Pauli matrices have a correspondence with so-called quaternions. All right? They are hypercomplex numbers. They are complex numbers having three distinct imaginary units which do not commute with each other. So you can just find the correspondence between the hypercomplex numbers called the quaternions with the Pauli matrices. They form the same algebra. Okay, there is an isomorphism, I guess, between Pauli matrices and the quaternions. Quaternions were discovered by Hamilton much earlier than quantum mechanics, I guess, in the 18th century, I guess. And these are discovered by Wolfgang Pauli in connection with the spin half particles, all right? But quaternions were already being discovered by Hamilton in previous century or maybe 200 years ago in connection with rotations. And Pauli matrices are connected to rotations in some way, right? So you can use this identity to calculate. So determine this thing here. Suppose at the exponential of, suppose, sigma z theta over 2 sigma x imaginary theta over 2. Calculate the same thing with sigma y and the sigma z, but of course the sigma z will be unchanged. All right. Well, let's change here by sigma y, so you'll find out what happens. So in this case, the sigma y is unchanged. Calculate, determine this thing. It's a rotation with respect to the y-axis. You rotate things with respect to the y-axis by an angle theta. All right. See what you find for after you compute all these things. For theta is equal to pi over 2, it's 90 degrees, all right, in the end. In the end, replace that value for theta and find out what emerges. But calculate for arbitrary angle of rotation. It's rotation with respect to the y-axis. So the n in this equation is the direction y. So it's 0, 1, 0. Or in vector notations, the direction of y. So find out what happens here. All right. It's a very interesting problem. Right. So I guess for Pauli matrices, that's enough for now, at least for now. I am anticipating it's connected with rotations, it's connected with spin half particles. They are very important in quantum mechanics. And next time, I guess I will talk about the Gaussian integration. After that, we will discuss the time evolution of in quantum mechanics. Bye bye.